Hi everyone, in this tutorial I will show you how to define radial magnetization in Comsol to model a permanent magnet with circular geometry. The example I will use is an array of magnets similar to what can be found in some types of DC motors. So the model is 3D and you will need a magnetic fields interface. In this case I have chosen MFNC. You can also choose MF if you wish to. And the type of study will be stationary. So first you can define some basic parameters related to the dimensions of the magnet. So TH for the thickness of the magnet, capital R for the outer radius of the magnet array, and L for the length of the magnet. I will change the units to millimeters, and then to construct the magnet, I will insert a work plane, and I will choose the YZ work plane. So first, let's create the outer edges of a single magnet. So I will insert a circular arc, define the outer radius, and the angle to specify the length, the arc length. I will duplicate this arc and subtract the thickness from the outer radius. Now this shape has to be closed using straight line segments. And then it needs to be converted into a surface. So under conversions, select convert to solid and then select all the edges. Click on build all. And then this magnet will be repeated 8 times. So under transforms, choose rotate. Select the input object, tick on keep input objects, and for the angle, we will specify a start angle of 0 up to 360 in steps of 45 degrees. So we will get a total of 8 magnets. Click on build all, and now you can see the cross-section of the magnet array. To simplify the meshing process, I will also insert 2 circles. This will help me to create a mapped mesh for the surface of the magnet. Okay, now we can exit the work plane, and then the magnet array can be extruded. Comsol automatically selects the work plane. The length is L. And then we need an air domain. So insert a cylinder. The axis type is along x-axis. So with that, the geometry is complete. Now, to define the radial magnetization, we need to insert a new coordinate system, a cylindrical coordinate system. So go to definitions and right-click, go under coordinate systems, and then select cylindrical system. So the diagram here explains all the different axes that we have. We will keep the center at the origin, but the longitudinal axis should be along the x-axis because that is the axis of the magnet array, as you can see on the screen. So we will change the direction of the longitudinal axis from z-axis to the x-axis. And in this case, the r theta plane lies in the yz plane. So we will change the value of x to 0 and y to 1. which means at an angle of 0, the radial axis will be pointing along the y-axis. So that's all we need to do to define the cylindrical system. And we can also create some explicit selections for the magnets. First, let's select all the magnets. And we'll also create a selection for the magnets magnetized along the radial direction and the positive direction. So I'll call them magnets N. These will be alternating. And the other 4 magnets will be called magnets S. Okay, and under geometry, under work plane, go back and tick on resulting object selection. This will also create an explicit selection which can be later used in the model. Okay, now we need to add the materials. Let's define air. The relative permeability will be 1. And for the magnets, we will insert the material from the library. Go to AC/DC, and under hard magnetic materials, you will find a bunch of or several magnetic materials that can be used. These are standard grades for permanent magnets. Let's select N52. These are neodymium magnets. Under selection, we will choose magnets, and you can see the properties are already defined, including the strength of the magnetization. Now we can go to the physics and insert magnetic flux conservation. If you have chosen the MF interface, you will need to insert Ampere's law. And all the other steps will be similar. So under magnetization model, select remanent flux density. And this will be applied to the magnets N. So magnetized along in the positive direction. And under coordinate system, we need to change global coordinate system to the cylindrical system that we created. So when you select that, you can see that the direction axes have changed, and we will keep this as 1, so magnetized along the positive direction, the radial direction. Let's duplicate this node and change the selection to magnets S, so the other set of magnets magnetized along the in the negative direction. The same cylindrical system will be used, but this time we will change the flux direction to -1 along the R axis. All the other properties, the strength and the permeability, is taken directly from the material that we inserted, and that's all we need to do for the physics. Now we can go to mesh and change the sequence type to user controlled. Insert a mapped mesh. Okay, the list is okay. From selection, choose work plane, and then unselect the center only. So this is a quick way to select the other required surfaces. Right-click on Mapped and insert Distribution, and select any one edge on the cross-section of the magnet array. So we need 5 divisions along the radial direction of the magnets. Change size to fine. Right-click on mesh and insert a swept operation. For the swept operation, click domain, and for the selection, choose extrude. And under extrude, insert a sizing node and change normal to finer. And then the free tetrahedral elements will be applied to whatever is remaining, which is the air domain. So after that, you can click on build all, and you can hide the outer surfaces to see the mesh from the inside. So you can see the mapped mesh which is created, and it is swept along the length of the magnet array. So that's all you need to do. And now under stationary study, click on show default solver. Make sure that all the required settings are selected. In this case, Comsol has chosen an iterative solver, which should work in this case. If it doesn't, you can activate the direct solver. So we will click on compute. The simulation should take a few seconds depending on the speed of your computer. And then Comsol generates the plots automatically. You can plot your own diagrams. Under 3D, you can choose a slice node, and then you can plot the quantities that you want to. So in this case, for example, the magnetic flux along the Z direction. So you can see the alternating magnetic flux, and you can also insert an arrow node to help you visualize the direction of the magnetic flux field. Insert arrow volume, and if you want to plot the arrow only at the center of the geometry, insert only one point along the x-axis, increase the number of points along the y and z-axis, and plot. You can change the color to make it more visible. So that's all for this tutorial. You can have any circular geometry. This would be the way to define radial magnetization. Of course, with the Cartesian system, it is still possible, but you need to enter the polar coordinates yourself. By going under definitions and inserting a cylindrical system, it becomes easier for you to define the flux direction in the physics. Thank you all for watching this tutorial.